So in this question we've got a student wanting to find the work lost or gained when two plates are moved apart, two parallel plates of a capacitor, and we've got this capacitor's got air between them according to the first part, and the plates each of area A are connected to a battery of potential difference V. Students set the initial separation of the plates to D1 and then move to D2. So here we go, this is the expression that they've found and we're aiming for that. First thing to note is that the work is the energy that has been converted. So work done is energy converted, and the energy conversion is going to be from mechanical energy that's moving the plates to electric potential energy in one way or another. Okay, so best way to look at this perhaps is to, because it's energy converted, the work done in this case will be the final minus the initial, E2 minus E1, so the energy difference. Yeah, and remembering that excuse me, energy formula for a capacitor is half QV. Oh gosh, better double check. Yeah, half QV. So in this case, what have we got? We need this energy formula in terms of capacitance, because that's what's actually changing. The distance is what's changing, so we need to find Q in terms of C, because we don't have a Q expression in here, a Q value in here. Not that that matters, maybe it cancels, who knows, but that's the instinct and we'll just follow that. So the capacitance is equal to charge over the voltage, so Q equals CV, which means our energy equation is going to go to half CV squared. So that's our general energy equation. Now we want to do this for each of the two distances. So we need to put in our capacitance formula in more detail. It's air gap, so we don't have the dielectric constant, so it's just epsilon naught area over D. Except in this case we've got D1 and D2 for this. So good way to do this, I guess, is to we'll just go straight into it. Work equals E2 minus E1, which is half C2V squared. I was going to put subscript there, but we don't need, minus half C1V squared. So same voltage, same half, which means we could take that out the front, but once we substitute the capacitance in, we're going to find that we have these extra, this extra term to bring out the front too. So we'll just substitute in the capacitance first, and then we'll simplify. So half epsilon naught area divided by D2 V squared minus half epsilon naught area, which doesn't change again, over D1 this time, V squared. So now is a good time, I think, to draw all of those common factors out of the front. We've got the half, the epsilon naught, the area, and the V squared. That's the same in both, and then we've got 1 over D2 minus 1 over D1. Just double check we've got everything. So double checking, we've got the half from both, we've got the epsilon naught from both, we've got the area from both, and we've got the V squared from both. Okay, that's great. Now that seems like a pretty good expression that covers all of it with just the one variable here. But we're just going to look at, up at the answers and see what we arrive at. So we've got the half, that's fine. We've got the area, epsilon naught V squared. But in here is a little bit different. We've got D2 minus D1 over D1 D2. So let's just look at that. That looks a little bit like something else I've seen before, which is the capacitance formula or the resistance formula for adding in series and parallel, depending on which one is which, but it's a 1 over plus So let's just take that 1 over D2 and 1 over D1 and see if we can do something with that to make this work out a little bit nicer. We've got, because we're going to have to do some cross multiplying to make all this come out, so I guess we'll just launch into it and see what we can do. Maybe it's actually easier to do this while it's in this form. So I'm just going to come off to the side a little bit and let's do our cross multiplying here. So it's going to be D1 times D2, D2 times by epsilon naught area V squared over D2 minus D1 D2 epsilon naught AV squared over D1. So the D2 and the D2 cancel, and the D1 and the D1 cancel, and then what have we got? We can okay, I think I might be going off on a bit of a sidetrack here that's not that helpful, because all we need to do is to change this section somehow. So rather than trying to follow that other pathway which was similar to the resistance formula, capacitance formula, I think we'll just treat these as fractions and try and form a common denominator and then add them together, because that's another thing that's what it looks like at the top. So to form a common denominator, you multiply the bottom by, so D1 times D2 is the most common denominator that we can find, because we can't work out any common factors of D1 and D2 except each other when we multiply them together. So if we convert this to, say, D1 over D1 D2, so we've multiplied the left hand side by D1 over D1, so you multiply them by 1, so you're not actually affecting the equation, and then we're minusing, we'll do the same thing on the other side, so D2 over D1 D2. So we've cross multiplied, we've multiplied this term here by D1 over D1, and this term here by D2 over D2, and since we're both multiplying by 1, it doesn't matter, and this gives us a common bottom number, common denominator. So then we can put them over the 1 like that and just call it D1 D2, and I think that might be what we actually get in the final answer, D1 minus D2 over D1 times D2. Let's go have a look wherever it is. So D2 minus D1 over D1 times D2, D2 minus D1. Okay, well they've got D1 and D2 back to front purely because of the difference, I think. So we've looked at the difference between the change in energy, and it's because capacitance is decreasing, it's a loss in energy, so it'll be negative, whatever the rest of it is, and that's going to lead to, so it's basically like having negative out the front of all of this, which turns one of them positive and the other one negative when you go through the process and calculate it all out. So there we go. At the risk of making the video longer, no, I won't make the video longer, we'll just put that in brackets and that part will go into here. Works, nice.